Well, I'd like to thank everyone for coming out again to Saturday Engineering. It's a great privilege to have everyone show up with so much interest in what we do, and it's an even greater privilege for me to introduce my friend and colleague, Paul Kwiat. So Paul is over in the physics department, and he holds a joint appointment in electrical and computer engineering. He is the Bardeen Chair and has been at the University of Illinois since January of 2001. Before that, Paul received his PhD from Berkeley in 1993, where he studied non-classical parametric down conversion, which is a fancy way of describing some of the stuff he's going to talk about today. He was the Lees-Meitner Fellow in Quantum Optics in the group of Anton Zeilinger, and then went on to Los Alamos National Laboratories as an Oppenheimer Fellow. He was a technical staff member in the Neutron Science and Technical Division, the Physics Division of Los Alamos. We were very lucky to attract him here, and I've been even luckier to attract him to this lecture series. Actually, Paul was kind enough to, when we were discussing this series and this being the International Year of Light, simply volunteer. And it's great to have him here. As you can see, there's an enormous amount of work that's gone into this. And without further ado, Paul Kwiat.
So, can anyone hear me? We're good? Okay, so thanks again, Scott, for the invitation, and thank you all for coming out on a very cold Saturday morning. If you guys have questions as we go, just wave your hand, yell out something polite, hopefully, and I will answer them as we go. My goal today is to tell you a little bit about part of my field, quantum information, and I guess I should have updated this to say the common person, because I hope this will be accessible to everyone, also our non-adults in the audience. And I have a habit of always changing the title, so really this is not going to be about IMAX so much, but about, in general, 3D movies. So not just IMAX, but the competitor to IMAX, the Real D 3D. I just want to take a moment to inform you that a month ago, one of the main people in quantum optics, in physics, passed away, unfortunately. Charlie Townes, who was one of the inventors of the laser, like this one that we have here, he passed away a month ago, and he was still kicking. He was 99, and I knew him when I was a graduate student when he was only 80, and he was coming in every morning, and my thesis is signed by him, which is kind of cool, but unfortunately he passed away recently. Okay, so the goal for the day is I want to explain how we actually see things in 3 dimensions and how that has evolved over the past couple decades with this binocular projection, and then talk about polarization, not the political kind of polarization, but light polarization, and then a comparison at the end of IMAX versus this Real D 3D. And that sounds like a lot, but really that's only the beginning of the story, so the rest of it then, this is my perhaps overly optimistic plan, is to talk now on quantum cryptography about how we send secrets and the fact that light is actually photons, so we'll be turning lights off for that and then talk about quantum cryptography. And my goal at the end of this is that you really should have an understanding of the basics of how quantum cryptography works, even though you're thinking you don't maybe know anything at all about quantum physics. So all of these work that I do in my lab, of course, I don't do anything in my lab. It's all done by my cadre of very stylishly attired students and postdocs, and one beagle. But I particularly want to highlight just a few people here who were very helpful in setting up all of this, getting together all of the stuff that you see here, and also Erica Smith, who's the head of the demo department, not the department, but in the physics department, we have a really good demo group for all the lectures. And so all of these things are things, or most of them, that you might see at some point in one of our undergraduate physics class. So just my overall philosophy, borrowing a quote from Einstein, is I really want to make things as simple as I possibly can. And so today, there will be no math. That's not quite true, actually. There will be no hard math. I think that's true. So this is pretty much the only math you're going to need to be able to do today. Yeah, so if we can get that, remember, so what is the answer to that, just to check here? 7. Okay, no cookie for you. Okay, so first question is, how do we actually see in 3D? And the simple answer is that we have binocular vision. So this is our first demo. You have everything you need. Hold up your finger. And now what you're going to do is close one eye and then switch eyes. Yeah? And then, you can, I don't care if you use your hand to do it. And now instead, look at my finger and close one eye and then close the other eye. And what you should see is that my finger doesn't really change much when you close one eye or the other, but your finger, because you're looking at it from really, really close, you get a totally different perspective. Yeah, so there's this notion that things that are, an image that's going to change a lot is going to be one that's closer. So if I have an object that's here, it looks more different to the two eyes than an object that's farther away. Okay, so that's going to be our simple answer for the day. The real answer is somewhat more complicated. We do use binocular vision, but also even people who only have vision in one eye still have a sense of depth perception. They use a lot of other clues, like how big things are. Things that are up close tend to be bigger than things that are far away, how things move relatively, the lighting that something has. Okay, so there's a lot of other features, but today we're only going to need to worry about this first one. So in a movie, so we'd like to be able to, in our movie experience, we'd like to be able to see things in 3D because it'll look more realistic, of course. The question is, how do we fake that so one thing you can do is you can have, if you want people to see, what will I say, a romantic comedy in 3D, what should you do? Sarah, what should you do? Well, maybe you could do a holographic, but a simpler thing that would have worked even hundreds of years ago if you wanted to see a romantic comedy. You go to a play. Good. Okay, so this is what I do in my classes. This is what I do in my classes to reward people for answering. I throw out candy. It also works for my dog, so it's good. Okay, so you go to a play, but now we don't want to have plays all the time. We want to be everyone to see Avatar or something like that. And so we want to somehow fake a 3D image with a 2D screen, and the way that we can do that is we can have a different image going to each eye, because that's what the eye expects when it's seeing something in 3D is a different image. So the question is, how can we do that? So those of you who are over 30 or over 40, how did we used to do that with 3D movies? You guys remember? Red and blue. Where was that? Where is that? There we go. Okay, right. So we have these red and blue glasses. And so the idea was that there would be two different images that are on the screen, a red one and a blue one, and then we only see the blue one through the left eye. We only see the, I don't like the way they did this. We only see the blue one through the left eye and the red one through the right eye, or vice versa. And so here's a picture from a 3D frame from a 3D movie, and you see the guy's head, which is sort of in the middle ground. You don't see a separation of the colors, but his hand, which is really close, you see the red and the blue are widely separated from each other. Okay, so I want to just talk a little bit about the basics of science and engineering here. So in the scientific method, I tried to break it down, thought about it a little bit this morning. What is it really? So in general, we have a question. There's something we're trying to understand, and we think about that, and maybe we come up with some hypothesis that's going to explain the thing we're trying to understand. And from that, then we propose some sort of an experiment that we can do to test that hypothesis. And that usually then is maybe going to lead to more questions. And then I'm going to have to form another hypothesis, and the thing is just going to keep looping through. And maybe we'll stay on the same topic, or maybe we'll sort of evolve to some other topic as we try to understand things. OK, so I want to compare that to what I might call the scientific engineering method, which is not that we have some generic question, like why is the sky blue, or where did the universe come from, or something like that, but really that I have some kind of a problem that I want to solve. And I'm going to then apply some experience with solving other problems, some insight, maybe a lot of the knowledge that's gained by doing science to come up with some sort of a solution, a proposed solution. And then we'll implement that solution, and that will probably lead to more problems. And then we'll have to try and fix them, and then we'll just keep cycling through until we get a solution that's close enough to solve the problem we want. So as an example, the problem that we had was we wanted to send different images to each eye. The solution that we were using was to use color filters So question is, what's the problem with this solution? Yes, yes, what's the problem? So if you go through color filters at different angles, the plastic ones actually tend to look pretty much the same at any angle. So that turns out to be OK. You could make the other filters that would be much more angle dependent, and then that would be a big problem. What else is a problem with the red?
It's changing the colors of your images.
Changes the color. In particular, let's say you're going to see Avatar where everyone is blue. You only see them on one side, and you don't see them on the other side, right? So that's not going to be very good for looking at color images. OK, so this leads us to our surprised-looking, shocked-looking girl here. OK, so I want a different solution for how we can go from one eye, from only showing one image to one eye at a time. And I'm going to show one now that was evolved quite a while ago for a whole bunch of different purposes. But in particular, you can buy now for your computer games. So they have a set of goggles, and the goggles are time synchronized to the projector or the TV, so that at any given time, the left eye sees one image, and then the right eye sees a different image, and then the left eye, so it toggles between which eye is actually viewing the screen. And then the image that's on the screen changes. So whenever I want the left eye image to show, that's only the left eye can see, the right eye is blocked, and whenever I only want the right eye image to show, only the right eye can see it. So that's a time synchronized version. So we only let each eye see at the correct time. So there are also problems with this. Anyone want to venture a couple problems? Yes, way in the back. Good, great. So it's a lot more hard to make these. It's not going to be super cheap to go into like an IMAX theater where there's hundreds of people. OK, heads up, it's coming to you. Pretty good. OK, any other things? Great, so something to do with frame rate. So there's two issues here. So one thing is that you're only seeing the light half as often because your eye is blocked half the time, so things are going to look dimmer. The other thing is that the fact that it's flickering, some people get nauseous from that a little bit, and so they can't actually watch these. So that's perfect. So now we want a different approach that's going to allow us to see things in a way that doesn't have those same, that may not have the same problems. OK, so now a brief interlude, a word from our sponsor. Why did I actually volunteer for this? I ask myself that all the time. And it's because of the fact that 2015 has been declared the International Year of Light from UNESCO. And in fact, they had a very nice quote, which I'm going to have to, I can't read my quotes when I'm actually on here, so I have to go down to this and say, International Year of Light is a global initiative which will highlight to the citizens of the world the importance of light and optical technologies in their lives, for their futures, and for the development of society. It is a unique opportunity to inspire, educate, and connect on a global scale. OK, so that all sounds, pretty good. I don't know that, IMAX 3D or whatever is hopefully improving your life in some small way. OK, so let me go back to this presenter view. And at Scott Carney's talk a couple weeks ago, he introduced me to a new word, the sesquicentennial. So 2015 is the sesquicentennial. Sesquicentennial means something happened 150 years ago. And the question is, what actually did happen 150 years ago? And the answer is that it was 150 years ago that a physicist, mathematical physicist, Maxwell, published a very, very important paper called A Dynamical Theory of the Electromagnetic Field. So I'm going to tell you more or less everything you need to know that was in this paper. It was actually very hard to understand, not an easy paper to get through, but it is now the central piece of all of our modern telecommunications and our understanding of light and electromagnetism. And Scott and I would be out of a job if this paper has not been written. OK, so here's the thing. There are electric charges. We know that there are electric charges. And the first thing is those electric charges produce electric fields. This something. I don't even want to try and explain what it is, but it produces an electric field. And those electric fields affect other charges. And that's how we can explain the repulsion of like charges and the attraction of different charges. So positive and negative charges attract. two positive charges will repel each other. And the way we understand this is the one positive charge makes an electric field, and then that pushes the other charge away. OK, so that's the first thing. The second thing is that if you have a moving electric charge, an oscillating electric charge, that will produce an oscillating electric field. I think that's maybe not so surprising. The third piece is that if you have an oscillating electric field, that makes an oscillating magnetic field, like kitchen magnet, that you have on your refrigerator. And then the final piece here is that if you have an oscillating magnetic field, that actually gives rise to an oscillating electric field.
Can you explain the word oscillating?
Oh, oscillating. Thank you very much. Thank you very much. So oscillating.
I'm not good at
It's all right. Oscillating just means moving up and down in this case. That's all I want, is something that's moving up and down. So we now see oscillating electric fields make magnetic fields, oscillating magnetic fields make electric fields, and we don't even need the charges now. Once we can start getting an oscillating electric field, that makes a magnetic field, which makes an electric field, which makes it a magnetic field, and that then gives rise to electromagnetic waves. They travel at c, which is the speed of light, and this describes radio waves, light waves, microwaves, X-rays, all kinds of things like that. So next thing I need to do is move to my other. I have a nice little thing to show that here, hopefully. Great. So here's my oscillating charge. It's moving up and down, and it's producing this oscillating electric field up and down. The magnetic field, it turns out, is perpendicular to that. We're not going to worry at all about the magnetic field today, so all we have to think about is this electric field that's moving up and down. Yep. OK, that's fine. So if we have then a go back to my presenter view here. So we might have a transmitter that might be, for example, an old TV tower. And in these wires here, the charges are being driven up and down on the wires. And then they're emitting electric fields that are also going up and down. And then you have your TV with its antenna. This is old school. You guys know what a TV antenna is? And you try to adjust the antenna so that you can get the signal, because the antenna has to be aligned so that the charges can move along it when the electric field comes in. A more new school version of this would be, for example, a little router. We probably have one somewhere in this room. And you might then have a little USB adapter that goes on your laptop to pick up that signal. And you can change the angle of that to try and maximize the signal. So pretty much no matter what school you're in, the point is you only get a strong signal when those antennas are aligned with each other. OK, so this brings us then to the concept of the polarization of light. So polarization of light is just the oscillation direction of the light wave, of the electric field. And we prepare and we measure it using a polarizer. And so I'm going to say a lot of stuff first, and then we're going to do a bunch of demos to make this look a little clearer. So we use a polarizer to either prepare it or to measure it. The polarizer is only going to transmit light that is along the axis of the polarizer. So I have a couple polarizers here. But maybe I'll just turn this on now. So here, this is polarized in this direction. And if I have a polarizer that's oriented the same way, my light gets through. If I have a I'll put it over here. If I have a polarizer that's oriented the same way, the light gets through. And if it's perpendicular, then no light gets through. Yeah, so it blocks it out. And this is the only equation, actually, I have, I think. No, this is one of two equations I have in the whole talk, which is that if I have some incident intensity coming in, the intensity that's transmitted is equal to the incident intensity times the cosine squared of the relative angle between those polarizations. OK, if you don't know your cosine squareds or something like that, don't worry about it. The point is that if the relative angle is 0 degrees, so if the two things are aligned with each other. In fact, actually, can you turn the lights off for this? We're working on it. Okay, there we go. So if the things are aligned the same way, which they are, then you get light, all the light gets through. If they are perpendicular, so if it's 90 degrees, then none of the light gets through. And if they're at 45 degrees, then half of the light gets through. Yeah, or minus 45 degrees, half of the light would get through. Yeah, and I could also show that maybe it'd be a little easier with these two lamps. So this is something which is vertical, and so if I take a vertical polarizer, everything gets through, and a horizontal polarizer, it looks pretty dark, hopefully, right? And same thing over here. This is a horizontal polarizer, so now everything gets through, and now it looks pretty dark, and in the middle it's about half the light gets through. Okay, so that's the only thing we need to know about this. And we can use that, for example, I'll do this last thing, and then that's used for sunglasses, for example, because there's glare. The glare typically is polarized. It's horizontally polarized, and so your sunglasses, if you have polarizing sunglasses, block that out. They block out the horizontal. And I have just a little thing that shows that somewhere. Is it there? It's not there. Is it there? Not there. Is it? Oh, there. Good. It is there. Great. So now I just have to find where this is. OK, so that's holding a polarizer and looking at the glare off the side of a car, basically. And if we rotate the polarizer, then we're able to completely block that out, because the light is highly polarized when it reflects off something. So that's why you pay extra money for polarizing sunglasses. I want to show a couple things on the other computer. If you can just do the, wherever my guy is. My guy's not, he's busy. OK, so I think if I go to laptop, VGA, south projector, VGA, south projector. Now, why is this? Where did it go? So we're trying to work on lots of computers at once. It's a little tricky.
Hope is on its way, Paul. Not working? No?
Of course, all these things worked when we demoed them earlier today.
Yes, of course they can. And it's deciding not to work. Is the VGA cable still plugged in?
Pardon?
VGA cable still plugged in?
It should be.
And the computer too?
Nothing's been touched. OK, so while he's playing,
So that works. VGA is not working now. Okay, yeah, if you would just.
OK, so I'm supposed to entertain you with a joke while he figures out what goes on with this. I just want to show, it'll be easier to see some pictures of how these polarization things, how they work. But actually, now that we have it, so you guys have your IMAX glasses, right? So if you put on your IMAX glass, we could certainly do that, and you look at these two things, if you have both eyes open, it's going to be a little confusing. But if you close one eye, you'll see only one of these, and if you close the other eye, you'll see only the other one. So the thing is, in your IMAX glasses, one of them is transmitting horizontally polarized light, and the other one is transmitting vertically polarized light. Yeah, so you can kind of see now how you can get a sense of how IMAX is going to work. It's going to work by sending one image in one polarization and the other image in the other polarization. How's it looking?
Paul, could I actually interrupt while you're doing
Please.
So at the end of today's talk, I'm going to give out a few topics, kids in the audience. So while we've got a little bit of a pause and try and figure out the electrical engineering here in the electrical engineering building, maybe I could, we ran out of full tickets. Do you have pieces with numbers on them? I'd like to give out all the kids in the audience while we've got a little bit of a break. So if you're a kid, or if you have a kid, raise a hand. If you feel like a kid,
No, no?
If you don't get one right now, I'm going to keep doing this whenever we have a little bit of a pause. And we're going to, one of the things that Paul does in his lab is he makes the world's best random number
Yay.
generators. We'll rely on him to pick a number. Okay, I'll play around. And
Cool.
I'll try to quietly hand these out if I don't.
Oh, you had it.
Before the end.
Yeah, but it wasn't on here, so you couldn't see what was going on.
I'll fake it. Okay, great. Thank you. Okay, so this is just a little applet that's showing, here's my incident light. It's vertically polarized, and if I have a polarizer that's 90 degrees to that, nothing gets through. If I make my other polarizer, instead of at 90 degrees, if I make it, say, at 45 degrees, about something like that. Okay, now half of the light gets through, and that's what this 0.5 is showing. And note that what gets through is then diagonally polarized in this case. Yeah? Okay, so hopefully I can go back to I can toggle between these things fairly easily. So laptop, HDMI, south projector, and we're back to here. Okay, so now this is how IMAX works. I guess you've already figured it out. So say again? Oh, yes. We'll come back to it in just a second, but for now we can turn it off. Thank you. And in fact, I can turn these guys off too, so you don't have lights going right towards you. Okay, so we send the different images are encoded in polarization, either horizontal polarization or vertical polarization, and you pick up only one of them with each eye. So question, what are the problems associated with this? Yes? Angle dependence, you maybe mean angle dependence if you're looking at it at an angle from this, and there is a little bit of that, although the screens do a pretty good job of catching that. But there's a different angle dependence that I will give another piece of chocolate for if someone can identify. Yes?
And if you tilt your head, then suddenly the polarization's all messed up.
So maybe that'll screw up the polarization if you tilt your head. So let me just turn these back on. Put your glasses back on. And now just rotate your head to the side. And now when you close one eye, you won't see just one of the two images. You'll see both of them, right? So you get crosstalk between the two. Yeah, so that's a bit of a problem. Okay, so we'd like to have a solution for that, and there is a solution. And that's going to have to do with, we want to change the polarization that we're using. So I'm going to think about if I could represent my polarization. So here's oscillating up and down, here's oscillating left and right. If I were to combine those two, I could get something that was oscillating at 45 degrees. And actually, can we turn the lights on? And this is the dance part of our show. You didn't realize there was going to be a dance part. And I'm going to ask my two volunteers to come up here. Okay, this is Sarah and Donna. Everyone say hi. Okay, over here. Quick. Okay, so Sarah's going to be the oscillating horizontal component here. And so her arms are going to be going left and right. That's going to be the field going left and right. Yeah, but to be able to synchronize things, she's only going to put her arm in a given location when I clap. So we're going to start going to the side, center, side, center, side, center. Okay, easy enough? Okay, my sister is going to be, Donna, is going to be the vertical oscillation. So she's going to start going up, center, down, center, up, center. Easy enough, right? Okay, so now we're both going to go at the same time. So first clap, second clap. Okay, stop. So we notice that now, if I combine these two things, I have something which is actually going diagonal this way. Yeah, and so if you just, we'll watch it a couple more cycles, and you'll see that we have something which is oscillating. Yeah, so it's oscillating like this. Let's say that I could somehow shift them so that they're no longer synchronized, that they're off by 2 clicks. So you're going to do the same thing you just did, and you're going to start going the other direction. Yeah, okay, so here we go. Yeah, okay, just stay there for a second. So notice that when I combine them going in the other direction, now I've got something which is oscillating in the other direction. Yeah? There's going to be one more that's going to be interesting for us, which is I'm going to shift them only by 1 click, only by 1/4 of a cycle this time. So you're going to start out in the middle. Yep. And you start out going up. So up. Yeah. I want you to do it one more. So I hope you guys kind of see that it's starting to move around. It looks like it's going around this way. It's a little harder since you're only getting the 4 points, but it's more or less what's happening. And last one that we'll do is again start at the middle position, but go off to the other opposite side. Yeah. Yep. Okay. So now again I have a circle, but it's going the opposite direction. Yeah, so if I can take these two components and change the relative phase between them, I can go from diagonal to anti-diagonal to circular to the other circular. Thank you very much. Super duper. Okay, so how do we actually do that in practice? Well, we'll use a material in which the horizontal and the vertical will travel at different speeds through it. And that's called a birefringent material. That can happen if you have a crystal where there's different atom spacings along one direction and the other direction. And one way that you can actually create such a thing, can we turn the lights off again? Is just using he has to run like all over the place to turn the lights on. Is there a thing I can do up here to get the lights? No. Okay, we'll keep the lights off for a few minutes this time. So I've got this polarized, and what I have here is just a piece of glass that has some tape on it, some cellophane tape on it. And if you just look at it, it doesn't look like there's anything amazing going on. But now what I'm going to do is put it between my polarizers, and we see that I see things now. I see things, and I see things in different colors. Why do I see things in different colors? Because of the fact that the speed propagation is a little different for the different colors. So whether things are exactly shifted by 2 clicks or 1 click or 3/4 of a click or some fraction of a click depends on the color. Another way that you can get this same sort of effect going on is if there's a stress in something. And so I'm now going to show, this is just a normal plastic lid of some kind. Sorry. Try and move it up so everyone can see it. There we go. And now I'm going to look at that through these polarizers. And you see we get all this extra information about where the stresses are in the plastic. Yeah, let me just do another 2 examples of that. Here's just a plastic spoon. Yeah, and if you take your IMAX glasses home with you, which you should, and you break them in half, so now you have 2 different things, you can look at all these different plastic things and you can see all these stresses, and you can play with this at home. Okay, the last example of that is one where I can actually change the stress. It's just a piece of plastic where I can squeeze it a little bit. And if I just squeeze it here, you can't see what's going on. But if I put this between these two and I squeeze it now, maybe I'll start this way. It's a little hard to see. Right at the corners, you can see it's getting dark. If I make this so that it's normally crossed polarizers, now when I squeeze, you can see where the stresses are. The stresses are right at the corners. And that's a way that engineers use to try and measure stress in different things. OK. So I want to go to the other thing for 1 second. Do I need to? Yes. Laptop, VGA, south projector. And just show you that we can make this circular polarization stuff and what that would look like. Not that one. Not. OK, this is fine. So here's showing the 2 waves when they are in phase with each other. So I get diagonal, and now I can change the phase of one of them with respect to the other one by 90 degrees. By 90 degrees. Boop, 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 boop. And now I get this thing which is circular, spiraling around circularly. And I think also maybe this last one, it's a different way of representing this different program that does the same thing. So you can see this spiral going on here. So I'm going to show just one more super cool demo because it's one of my favorite ones. So I have here just two cross polarizers. And I'll just turn the lights on to this. And I have here just an ordinary glass, and I have some corn syrup, sugar. Sugar is a handed molecule, and so it has different speeds for the light that's clockwise and the light that's counterclockwise. They go through at different speeds. And I'm just going to, oh, this is actually sealed. So this is a real-time demo. That's always a dangerous thing. Because I don't really want to put my hand in the sugar solution. This is like terrorist proof or something. Okay. Okay. So I'll just rotate this around so you guys can see this, because it's really pretty kind of beautiful. And if I change the background, you can get a kind of the complementary pattern that's showing up here. Yeah? And you see different colors because, again, because the different colors are going through at slightly different speeds. And it's different depending on where you're going through the glass because you're going through different thicknesses of the sugar solution. So you get more or less of this effect that's happening. OK, so now we are ready. Remember, this is all about IMAX and 3D movies and things like that. So let's go back to that. Remember, the last problem we had was that in IMAX, if you rotate your head, you get a problem in that you see both images. And so what we can do then, let's go back to HDMI, self-projector. So we can use this circular polarization, and that's what's going on not in IMAX, but in the competing technology, the real D 3D solutions. And so I have actually a bunch of glasses from there. And if any of you want to pick one up afterward, we can do that. I don't think I want to try and distribute them right now. But no, those are the IMAX ones. And then I do have some of the other real D 3D ones. It's the other competing technology, not at IMAX. And that's actually what I have set up here. If you were to look, I have the glasses in front of the light bulb. So this is actually sending out left circular, and this is sending out right circular, or clockwise circular and counterclockwise circular. If you look with your IMAX glasses and you rotate it, you won't really see much. But if instead you look with one of the real D ones and you close one eye, you'll only see one image, you'll only see the other image. Actually, maybe I can do that. I guess I could do it this way, just by putting these. I guess at this stage now, you should only one of them should be coming through to you. Let's see, circular, circular. Yeah? It's pretty sensitive to I have to get the orientation pretty careful. OK, so that's what's going on in terms of the real D solution. So they're projecting, and they're using only one of the two polarizations. Yes?
If you take these glasses in the IMAX, then you don't have a problem with the head.
Yeah.
So if you bring your own glasses, you'd be OK.
If you bring the IMAX glasses to the IMAX theater, you'd be fine. If you
brought the real 3D,
then they won't do anything. You'll see both images all the time with both eyes, and so that's not what you want. So what they do is they alternately send either the counterclockwise or clockwise image to the screen, and then you see only one of the images with one eye at a time because the left eye can only see clockwise, the right eye can only see the. They have to do it faster than the refresh rate of the eye. I think they do it at, I think it's 40 hertz. I'm not exactly sure. But again, people can get nausea because of that. And in fact, that's certainly another, so they're alternating between the clockwise and the counterclockwise images. And so it's insensitive to tilt. There are problems. The main problem is that you're only getting half the light to each eye again, so it's quite a bit dimmer than it would be in an IMAX theater. Yeah? In fact, if we just do a comparison, the IMAX actually uses two projectors because it's sending both the polarizations at once, whereas the other one, they have one projector and they just toggle between the two. So it's quite a bit dimmer. OK, So remember, this was actually all about quantum information and quantum cryptography, so that's what I want to talk about now. And I've just indicated here some of our funding agents for these things, including like the Disruptive Technologies Office, the National Security Agency. So there's a lot of interest in dealing with codes. And so that's the program for the rest of the day, is understanding how we can send secrets and how we can use everything that we already know to do that. OK, so the whole point about cryptography is that we want to have a message that only the intended recipient can understand. So here's my so-called practical example. So let's say we need to get a new pope. And one of the cardinals who's voting can't make it to Rome. So the question is, how can he send his information securely to the Vatican? And there are two ways that he can do this. One, he can use so-called public key encryption. That's what we currently use on all your internet transactions. It's sort of the standard way. Unfortunately, it's not provably secure. And in fact, if there were a quantum computer, then all of those things are absolutely not secure. And if, for example, the NSA really wants to know what you're sending and they put all of their supercomputers on it, then those codes can be broken. OK, so the other method is so-called secret key encryption, and that is going to be provably secure as long as it's properly implemented. There's no way to crack it. So here's how this is going to look. So we have to assume that the person who's trying to communicate with the Vatican, that he has a key with the Vatican. The key is just a random string of zeros and ones, completely random string of zeros and ones that he knows and that the Vatican knows. And then he's going to take his choice for pope, let's say it's Bob, and he converts that into a binary string of zeros and ones. So here's B is represented by 0110010, and then here's O, and then here's the same string again for B. And now he's going to add the key to the message bit by bit and modulo 2. So that means 0 plus 0 is 0, 1 plus 1 would be 2, but we wrap it around to 0 again. 0 and 1 is 1. So I'm going to end up with a string that's still just zeros and ones. And then he sends that over some public channel to Rome. Yes?
So how do you tell if the 0 that the guy in Rome gets is a 0, 0 or a 1, 1?
They have to start out with the same random key. And we assume that they have that to begin with. And that's going to be one of the big troubles, I guess. OK, so he sends this ciphertext over to Rome. Anyone can intercept this because this is just a random string of zeros and ones, because although the message wasn't random, the key was completely random. So it's just a random string of zeros and ones. There's no code to be broken. Take your best supercomputer. There's nothing to be broken here. The Vatican just does the same thing again. They take the ciphertext and they add the key modulo 2. And if you just run this back up, you'll see that you get the original message. OK, so the hard problem then is, how do you share the key? How do you get the key from Alice to Bob? And this is where quantum cryptography comes in. It's basically a way of distributing this random key. OK, so we need to take another quick overview now. Now we're going into quantum mechanics land. And it was in 1905 that Einstein made, pardon the pun, a quantum leap, basically starting off quantum mechanics when he proposed that light was really made of particles. This was not really well taken at the time. I would say it really wasn't believed initially because people knew that light was waves. We've just been talking about light waves, right? So people knew that. Anyway, they have very small energy. This is the only other equation in the entire talk. So the energy of a photon is this very small number, Planck's constant, times the frequency of the photon. Or in terms of the wavelength, I could write it as Planck's constant times the speed of light. So just to put this in perspective, a 1 milliwatt red laser, this is a green laser, but it's about 1 milliwatt, would have something like 3 times 10 to the 15 photons per second. So that's how many photons per second. So that's a lot, right? So photons are pretty small. That's a very big number. Your eye cannot resolve those individual photons coming in, although the rods in your eye do detect single photons, and it's possible that you may be able to see single photons, and we're in fact trying to determine that in my lab. And if you want to help us and volunteer with that, come see me afterward, and you can help sit in our chair, and we'll dark adapt you for an hour, and then send single photons and see if you can see them. OK, but talk to me about that afterward. OK, so light comes as photons. And now the last thing we need, and then we're done with everything we need, is to connect what we already knew about polarization to photons. So for classical waves, we said the polarization was the oscillation of the electric field. We can prepare and measure it with a polarizer. And then there was this fact that the transmission probability went like cosine squared of this relative angle. OK, for photons, the polarization we have to view as just this intrinsic property of a photon. So it's not some thing that's oscillating necessarily. It's just a property. Again, we prepare and we measure it with a polarizer. And the probability to be transmitted through a polarizer instead of being an intensity is just, the probability is just cosine squared of the relative angle. So it's the same thing that we already had. If I have a horizontally polarized photon, how do I want to do this? If I have a horizontally polarized photon like I do here, and I have a vertical polarizer, then nothing gets through. If it's a horizontal polarizer, it gets through with a 100% chance. And if it's a diagonal polarizer, then it has a 50% chance for the photon to get through. And the photon either gets through in its entirety, or it doesn't get through at all. And it's completely random which of those things happen. And any photons that get through are then polarized just like the polarizer was. So if I have a horizontally polarized photon, and then I go through a diagonal polarizer, if the photon gets through, then it's diagonally polarized. And it doesn't remember what it used to be. OK, so that's all that we need. And I wanted to show just one other demo about the fact that there are photons. So how do we see that there are photons? We have detectors that can see single photons. They're sensitive to single photons. And what I've done, I have to plug in my last cable here. Cable. OK, so this is a single photon counter right now. And I've hooked it up to some speakers. And anytime it sees 100 photons, then it makes a click. So anytime you hear a click, that's 100 photons that are being seen by this. This whole thing is just because I couldn't dim the lights in the room enough. The room is really super bright. And so this has a little tiny hole in the end of this aluminum foil so that there's not too many photons coming in. But if, for example, I just have my cell phone light on, then we can easily pick that up. Yeah? Again, I have a lot of shielding on this. If I were to just pull this out and expose it more to the room, even though it's not very bright in the room, that's all the light coming through my thumb right now. Yeah, so this is what 10 to the 15 sounds like. OK, sounds annoying. I get it. OK, I'm going to skip this one slide. No, I'm going to spend 1 minute talking about it. How quantum information is different from classical information. So classical information we represent as binary digits or bits, zeros and ones. You can copy classical information. We do that all the time. Quantum information we say is encoded in quantum bits, where quantum bits can be 0 or 1 or combinations of 0 and 1 at the same time. It turns out you can't copy quantum information. And one of the main differences is how we would represent quantum information. Classical information, something's either a 0 or a 1. But in the quantum case, we can have 0. So I'm going to represent my quantum bits somewhere on the surface of a sphere. So I could have 0 here, 1 on the other side, 0 plus 1, 0 minus 1, other combinations everywhere on the sphere. You may be thinking, what does that even mean? If we think about polarization, we could have horizontal, vertical. We could have diagonal as a combination of horizontal and vertical at the same time. The circular is a combination of horizontal and vertical. So the point is there's just a lot more options when you're dealing with quantum information than classical information. OK, so now how we can do quantum cryptography. We want to have a single photon source, because that's basically what I'm going to do. I'm going to encode the information of my key using single photons. It'd be good if we really had single photons. Typically, we maybe use an attenuated laser pulse, so that only on average there's one photon. We need to have distinguishable states so that we can encode either the 0 or the 1. And we need to be able to detect with some sort of a single photon detector. So maybe we have an attenuated laser pulse, and then we'll use horizontal polarization to encode a 0 and vertical polarization to encode a 1, and then those are just sent from the sender to the receiver. Yeah? And so that sounds good. I can send 0s and 1s that way. There's a problem, though, in that if there were an eavesdropper who's trying to get the information about what the key is, the eavesdropper could just sit in the middle, and she could measure the polarization of every photon that's being sent, and she measures it whether it's horizontal or vertical, and then she just sends on another photon onto the receiver. So she intercepts the signal, she finds out what the polarization was, she found out whether 0 or 1, and then she sends something on to the receiver, and he gets exactly the same thing that would have been sent anyway. And so there's no way to detect that there's an eavesdropper in that case. So this would not be a good way of doing encryption, because you could have someone listening in and you'd have no way of knowing that that was happening. Okay, so here's the final trick. We need to send some of our photons in a superposition of horizontal and vertical, and then in that way we can confirm that there hasn't been any eavesdropping. So a superposition of horizontal and vertical, for example, is we send diagonal. So I have a little movie that's going to hopefully explain how this kind of works, and then we'll talk about it for a couple more minutes. So I'm going to use perpendicular polarizations to encode 0s and 1s, either in this horizontal vertical arrangement called a basis, or in this diagonal, so plus 45 or minus 45. So here's the sender and the receiver. The sender sometimes we call Alice, and the receiver we call Bob. So she's going to send every one of her photons either with the horizontal or vertical or plus 45 or minus 45. And then on the receiving side, we're going to measure and ask the question, is a photon, we can only ask, is it either horizontal or vertical, or we can ask, is it diagonal? So if the receiver uses the same basis as Alice, he'll measure the same polarization. So if she sends horizontal and he's measuring, is it horizontal or vertical, he'll measure horizontal. If she sends minus 45 and he measures is it plus or minus 45, he'll measure the same thing that she sent. So then they talk over a public channel, and they identify which ones that he saw, and in particular, what basis he used. Yeah, so they'll identify, did they use the same basis or the different basis? If they use the different basis, they completely discard the results, because then there's no correlations at all. So it's only if they use the same basis that they'll have correlated information. But if they use the same basis, then whatever was sent by Alice has to be the same thing that was received by Bob. So if she sent horizontal and he measured horizontal and vertical, he got what she sent. He got horizontal. And if she sent plus 45 and he measured in the 45 minus 45, she would have got plus 45. And then they simply agree to identify horizontal and say horizontal and 45 with a 0, and vertical and minus 45 with a 1. And at the end of the day, now they have exactly the same random key that they can use. OK, so what is eavesdropping? What happens with eavesdropping here? Well, first of all, there's no possibility for an eavesdropper to tap the line to pull off some of the signal, because if she takes a photon and it doesn't make it to the receiver, if it doesn't make it to the Bob, it never becomes part of the key. It's not possible for her to make a copy of the photon, and then, so you could imagine maybe she makes a copy of it, she sends the original on to Bob, so he doesn't know that she was there, but it turns out you can't copy quantum information. That's one of the main principles of it. So she can't do that. The best thing that she can do is she can make a measurement, but if she makes a measurement and she measures it the wrong way, then she'll introduce an error. And this is where I have this thing where it says non-hard math here. OK, so last polarization demo here. So let's say that Alice was sending horizontal and Bob was measuring vertical. Yeah, so Bob should not see anything. True enough, right? But now we have the eavesdropper in the middle, and if she makes a measurement in either the measure with either horizontal or vertical, I'm just going to put this in between, they still don't see anything. Nothing comes through. But if instead she happens to measure diagonally, then where previously nothing would get through, now some of the light shows up. Okay, let's just do a quick test here. So I've got horizontally polarized light here. What's the chance that it would get through a 45-degree polarizer? It's 50%. That's what I said, right? And now I've got any photon that got through the eavesdropper's diagonal polarizer is now diagonally polarized. So what's the chance that that would get through this vertical polarizer on Bob's side? It's going to be 25%, right? Because I have to multiply a half times a half. And when you multiply a half times a half, which one of you guys said it? You get 25%. So if there's an eavesdropper in the system, she will introduce, and she's measuring things, she will introduce a 25% error in this key that's being generated. So we just have to check to see that if there are errors, and if the error rate is too high, we know the key's not secure, and then we just never use an insecure key. So we never use the insecure key to do any encryption, and so that's why this is perfectly secure. Okay, so the current world record for this, what's too high? So there are some tricks you can use to, if you know the amount of errors that you have, roughly speaking, the eavesdropper knows 5 times as much, whatever the error rate is, or 4 times as much. So if you have a 25% error rate, she knows everything. If she were to only measure like 1%, or let's say 10% of the data, then she'd only introduce a 2.5% error rate. And then you know that she knew 10% of the stuff. And so from knowing what the error rate is, you can know how much she knows. And then there's some classical tricks you can use, classical processing techniques to reduce the amount of information she knows, as long as your total errors are less than about 10%.
So without comparing their keys, how do they know whether an error was introduced or not?
Oh, great question. So how do you know that there's an error if you don't actually compare their keys? And the answer is that they have to sacrifice some of their key data. So they take, let's say, you do it at random, but it's easier to think about. I'm going to take the first 10 bits of the key and just announce, oh, it was supposed to be a 010001. And on the receiver, he says, yes, that's what I got. We're good. Or he says, no, I was off on 2 of those. And it's okay, it's probably not secure. So they have to sacrifice some. And you wouldn't do just the first 10 because you assume that an eavesdropper maybe knows which. If you were always going to do the first 10, she would know that, and she just wouldn't look at the first 10. So you pick at random later on which ones you check. OK, great questions. Other questions? OK, so the current distance record for this in free space is 144 kilometers between 2 of the Canary Islands. That's because they have telescopes that can point directly at each other. We have a project in my own group that just started about a year ago with the Navy trying to generate quantum keys between ships and maybe eventually between ship and some sort of aerial vehicle. This is with a number of other universities trying to do this, and we're tasked with trying to go send quantum cryptography over the water, over the sea deck, out to something like 100 million bits a second, which is a bit of a challenge. So as always, let's come back to this. What are the problems associated with this? Can anyone make a guess what the difficulty of doing it from a ship compared to the original experiment that I just showed where people were on the Canary Islands? What's one big difference? Yes, right in back. Pardon? The ship is always moving, and in particular, the type of motion is going to be what's important to us. So the ships sway in the water. And that sway is going to introduce polarization errors in exactly the same way that when we were doing this with the IMAX and you tilt your head and you got both of the signals coming through. Yeah, so if we're encoding using horizontal and vertical, that's going to introduce errors. So here's what this string was supposed to look like. If we tilt by 5 degrees, then we get about a 1% error. If we tilt by 10 degrees, we get about a 3% error. If you tilt by 15 degrees, you get about a 7% error. And remember, I said actually 10% is pretty much the level where you can't do anything. So that's getting pretty serious. So can anyone tell me what the one solution to this is? Yes, way back there. Oh, so you could certainly, yes, you could certainly put in some technology that would try to keep things level, but we'd like to see if there's a solution that doesn't require that based on what you already know. A different polarization, in particular, what kind of polarization? I should use circular polarization. Because in that case, then, to do the encoding, in that case, it doesn't matter if the ship rotates because the clockwise, even if the ship rotates, still looks clockwise. Counterclockwise, even if the ship rotates, still looks counterclockwise. There's another trick that we might use, which is to use the original type of 3D encoding where you have synced glasses. So basically, I'll have two time bins, an early and a late time bin, and if the photon comes in the early time bin, I'll call it a 0. If it comes in the late time bin, I call it a 1. In that case, then it doesn't matter if the ship is changing. I'm just telling when it's coming. So it's just like when we had the glasses that were flipping, where you could only see with one eye or the other eye. Yes?
Aren't you limited by the line of sight?
Yes, you're absolutely limited by line of sight. And fog is a really big problem, and loss can be a problem. So yes, that's why you can only go about 30 kilometers, because otherwise the curvature of the Earth gets in the way and you hit the water. You know, you are just like way ahead of me. I don't know. Did I make it? Did I kill anyone? Hopefully we're good. OK, so one thing to deal with the low loss rate is we can use color multiplexing. So in other words, we can send with different colors. We can send one channel in red, a different channel in blue. It's kind of like using the old 3D glasses. And that allows us, if instead of 2 colors you use 20 different colors, then that increases the rate at which you can do this by a factor of 20. I want to check one thing, and then I'm going to do. Oh, it's hidden. OK, so since you asked, unhide slide. Since you asked about couldn't we go up to a satellite, and the answer is yes, one can go up to a satellite or try to go up to a satellite. And the advantage is that then you don't need a line of sight. You just have to use a satellite. And in fact, there's kind of an interesting protocol. As long as 2 people can see the same satellite, not at the same time, but just at any time, they can generate the key. So the thing is that I'm looking at the satellite. Sorry, Alice, my sister's looking at the satellite over in Ohio, and she generates a key with the satellite. And then a while later, the satellite comes over me, and so let's say a 1,000-bit key. And then a while later, the satellite is over me, and I generate a key, a quantum key with the satellite. And then the satellite simply tells me which bits of my key I need to flip. So the satellite tells me if I want to have the same key that she had, the key is just 0s and 1s. I need to flip bit number 2, bit number 3, bit number 7, 8, 9, whichever ones are not in agreement. And then I flip them, and then I get to have the same key that she does. And once we have the same key, then we can do this encryption. Announcing to an eavesdropper, flip bit number 2 does not help the eavesdropper if she didn't know what bit number 2 was to begin with. So saying flip bit 2, she doesn't know if it was 0 or 1 to begin with, so she doesn't know if it's 1 or 0 afterward. So that becomes safe as long as you trust the satellite. And I just want to put another plug in that we also have some money from NASA to try and put a project on the space station to do quantum communication from the space station down to Earth. OK. I think I'll just say that quantum cryptography is now in commercial use. There's a couple companies that sell systems. They tend to use optical fiber instead of free space because we have this whole optical fiber network. It's been used to secure elections in Geneva. Tokyo has a network. It's been used for some banks in Switzerland. And just recently, it was announced that China is building a 1,200-mile link between Beijing and Shanghai using this quantum cryptography stuff. This is just a very recent paper. I included, oh, do I not have the date? Yeah, February 9th, 2015. So this is the current world record of how far you can send quantum cryptography and optical fiber. One of the things that limits you is that if there's loss in the fiber, you can't put any amplifiers in because that would be like trying to clone. And so pretty much you have to send one photon in at the beginning, and it has to make it to the end. Otherwise, you're in trouble. I'll just say the last thing, which is that in general, you don't use polarization in a fiber because the fiber can change the polarization. If there are stresses in the fiber, it changes the polarization exactly the same way that piece of plastic changed the polarization. So instead of using instead of polarization, they use time bins instead. But that does have a problem, because if you use time bins, then you have a lower rate because you're only sending half the time. It's the same way that when you're in the real D 3D, when they're toggling between the two images, it looks dimmer to you than IMAX would, because they can only send one of the two things at the same time. OK, so comparison between IMAX or 3D and quantum cryptography. The goal is very different, of course. In a movie, we're trying to transmit information to many, many people. And in quantum cryptography, we're trying to send to just one. We want to have a very bright projector for IMAX or for a 3D movie, whereas we want to have ideally single photons for quantum cryptography. We use, obviously, the human eye for movies, and we need these fancy single photon detectors for quantum cryptography. We can use the same sort of polarization encoding, except that in quantum cryptography, we have to use not just, say, horizontal or vertical or left or right circular. We have to use two different bases at the same time. In both cases, if you use the circular polarization, you're insensitive to any kind of tilts. Well, you can use timing instead, but the timing is technologically harder. Timing is where, for example, we use the glasses where it just only allows light to go to one eye or the other eye at a time. And in both cases, I'd say they're fun and maybe entertaining and profitable. Probably IMAX is more profitable than quantum cryptography at this stage. But OK, so my last slide, if it actually decides to come up. Another quote from Einstein. So if any of you have other questions, maybe I'll take two questions. And then, Scott, you want to do the
Yeah, actually, Paul, while you're taking questions, I just want to take a quick look at the audience again. Were there any kids, people who feel like kids, or kids who have kids? People who have kids. No, if they're kids who have kids. Yes. Great. And Paul, please do take questions.
Yeah, OK. And can you turn the lights back on? Yes.
Keep those hands up.
So that was, I see. I can't tell what's a question and what's someone.
Oh, yeah. Oh, yeah, that doesn't
Way in
really
the back.
work, does it?
What about there's Game Boy 3DS that doesn't use any glasses? Is that related to this at all?
Did you get a number?
Is that not related?
No, if it doesn't use glasses, it's using a different, it's relying on a different technique that has to deal with parallax, I believe, and so it only works from a certain angle. But it's really totally different. You're not encoding two totally separate signals that are going to the eye. Other questions?
For like the satellite communication, you're not shining a light at the satellite. It's using the computer binary information to transmit it. So like the relationship here between IMAX and quantum cryptography is really that quantum state being is on or is off.
It's that we're using some property of the light to encode two different types of either 0 or 1 in the quantum cryptography, or left eye and right eye in IMAX. And you can do that by using, in IMAX, you can do that by using horizontal or vertical polarization, or by using left circular or right circular polarization, or by using signal coming in an early time slot or a late time slot. And the same thing is true for the quantum cryptography. So in that sense, it's the same.
So, Paul, could I get you to act as my random number generator?
Do you want me to just pick a number, or you want me to just close my eyes and pick a piece of paper?
I want to quietly tell you which one slipped me a 20. And then, OK. So a number between 12 and 32.
A number between 12 and 32. 5 pi?
Ah, an integer.
15.
15. Do we have number 15? Number 15, are you here? See me before you go.
Another number?
Another number.
Between 12 and
Yeah,
32,
yeah.
but,
One more. Yeah.
but not 15.
But not 15.
29.
29? Oh, yeah, 29. Excellent. And one more.
What's the lowest range? I'm trying to think. 12. OK, the temperature today, I think it's supposed to get up to 20?
Fahrenheit.
20 Fahrenheit. 20.
20. Do we have number 20 here? 20? Are you here? Is that you? OK, excellent. So all three of you, see me on your way out before you go. You're all getting a Light Blocks optics kit. You can do polarization experiments with it, color experiments with it, and some good old imaging and lensing. OK? And you must share with your sisters, too. OK? So, Okay.
Other questions?
I'll
Yes.
take one. Yeah, let's do another question while we have time. No more questions? Well, yes, one right back in the corner.
Yes.
So you solve the eavesdropping problem by going from up and down and left and right to like the diagonal.
Uh-huh.
And then you solve the tilting problem by doing those rotations. But the rotations, wouldn't that reintroduce the eavesdropping problem? Because there's only
Yeah, so, okay, you can come up and claim chocolate afterward, yes. So if you only use, yes, so I swindled just a little bit. If you only use the circular polarization, then you don't know if there's an eavesdropper. So you also have to then check in, say, the horizontal or vertical polarization. The eavesdropper will, if she's measuring in the circular case to try and figure out what you're doing, she'll introduce errors in the other ones, but as long as you're not swaying too big, you can still get a sense of whether or not that you can still put limits on whether there's an eavesdropper in. Yeah, but it is slightly more sophisticated than I had originally said, and you caught exactly the issue. So, chocolate.
It sounds, you say provably secure,
Yes.
but only within a probability.
How do I want
Then
to?
you can drive to infinitesimal, but
Yeah, so it's provably secure in the following sense. One, mathematically, if there's a random key that both people have and no one else has it, there's no way to break any code because there's no code to be broken. So it's mathematically provably secure, very different than what we currently use for our public key encryption. The second thing, though, is how do I know that no one else has that key? And then that's where I said if it's properly implemented. And people have done hacks on quantum cryptography systems already, where, for example, you shine a light into the eavesdropper, shines a light into one of the detectors and blinds that detector so that it can't see anything. And then she knows that the next detection is going to be on a different detector. So instead of on the horizontal detector, it's the vertical one. So you have to put things in place to ensure that that's not going to happen. And also, when you're checking for an eavesdropper, you want to know what the error rate is. Let's say you measure a 1% error rate, but if you only have a few counts that are coming in, you don't really know that 1% very well. Maybe it's really 4% or something. So you have to take that into account when you're doing the analysis.
So I'm sure that people have plans after the talk, but I know that Paul is incredibly generous with his time and will stick around and answer questions.
Yes,
Will you?
absolutely. Yeah.
And there was one quick question as to if you didn't win one in a drawing today, could you go out and get one of these? Yes, from the Optical Society of America. If you bought a computer that has the Google on it, if you Google OSA and light blocks, you'll find it immediately. Or you can email me. My last name is Carney, and I'm just carney@illinois.edu, and I'll be glad to send you a link for it if you're interested. Paul?
I want to say just one more thing. So please, if you want, you don't have to take the glasses. If you want, you just leave them by the boxes by the door. But if you want to take them, take them. You can play with them. Other things you can do, if you look at the sky, for example, when the sun's behind you, the sky is actually polarized somewhat because of how the light reflects off the sky. In fact, that's how bees find their way home. They use the polarization of the sky. So you can look at that. You can look at reflections off of different elements, off of different things, and you'll see the light is polarized. So, become a scientist and explore. Thanks so much for your attention.
Let's thank Paul again. Thank you, Paul.
Illinois.